All right, folks, so let me switch. All right, so today is February 18. The midterm exam is coming tomorrow. So I think everyone is already ready for that. So that's why not so many people came to the office hours, because they have no more questions, I guess. We have 3, 6, 8, 9 students in here, and 7 of them online. So let's see if they have questions. Also, we can go there and answer those questions. So do you have any questions for me at this moment? Yes.
I have a question.
Yes.
Can you go over the peptide kind of planes, like how many peptides are in each plane?
Okay. So peptide planes is one question. Anything else relate to that or separate from that? Yes.
Can you go over how to estimate the PI of a protein?
Okay.
The polypeptide?
Yeah, maybe I start from this one. Okay. So let me do something in here. Let me share some. I want to make sure that there's a little delay on YouTube, right? So I want to make sure that we have the right thing there. Yeah. So let's name this peptide and then we answer that question. Okay. So that's the question is that how can we estimate? I think it's based on the question that I sent over the Valentine's Day, right? That I sent a question. And that question is related to something that we did in class with insulin. Remember that when I talk about insulin, I said, oh, there's another variation of insulin. There is insulin glargine and insulin aspartate. Remember those? And then I mentioned that insulin glargine has 2 R residues, 2 arginines, right? So arginines are a basic amino acid, right? So therefore, the PI goes up because it's basic. So basically what you have to do is to look at a sequence, and if you find that there are basic amino acids, then we can guess without calculating, oh, this thing is going to go up. And if there are acid residues, then we know that's going to go the other way, right? So let's write the name of this peptide here, and then we go from there, okay? So let me take this thing out. All right, so this peptide here, very simple, right? We have the amino group here, and the carboxylic group there, the C-terminus, correct? Will take a while for you to see because of the delay of YouTube. Anyhow, so I see a question there before we catch up with that. Can you go over 3 and 10? To me, this is the worst type of question to answer because I want to answer, but I don't have any idea what's 3 and 10 unless you tell me specifically. So when you go to these chats online, don't be vague because in front of you I don't have all the exams in front of me. I don't know what's 3 and 10, right? No matter how much I want to help, I can't help. So if there is a chat, ask specific questions, okay? Make sure that, problem 3, there was such and such issues, and it was about such and such. Can you tell me something, okay? Because I don't have all the questions in front of me. Anyhow, going back to the peptide here, so what we have for this peptide? What's the first amino acid residues here? I'm going to take the out here, the rest is going to be annoying here. The delay. All right, so anything else here that we can do to solve this problem? What? This one, alanine, and the second one? Serine. Right? And then the next one? Histidine. And follow that? tryptophan. And the
Glutamic acid.
after tryptophan was, what was that?
Glutamic acid.
Glutamic acid. And then,
Ascorbic acid.
yeah, let's write this thing down, right? So that the first one was alanine. Write a little bit thicker today for the. So it was alanine, and then the second one was what? Serine, right? Serine, and then histidine. And next, tryptophan, which is W. We are in here. Oh, we are not there. We are here. Now the next one is going to be this guy here.
Glutamic acid.
Glutamic acid, which letter is that?
Yeah.
E.
Oh.
E, right? And then the next one is acid also, but it's aspartic acid, right? Aspartic acid, which is D, right? Aspartic acid. And after that one, we have here CH2, NH2. Kind of the picture here is a little bit covered, but that's what we're trying to find out. What's that?
Aspartame.
Which letter? Which letter is that? Which letter is this one?
N.
N, right? There's N and Q. Q is the one with 2 carbon, right? So this. And next one is E, right? E. Serine again. Another aspartic acid, which is D. Another alanine here. And the last but not least, tyrosine. So Ash Wednesday. I've been always in classes showing this peptide that makes some sense. For example, today is Ash Wednesday, right? But in the exam, it's not going to have any meaning, okay? Don't be surprised. You say, oh my goodness, I'm doing something wrong. I can't find any words associated with that. That's not the case. It's just because it is not like that. I should have written a peptide that would say a name, but I end up not doing that. Now, then we can answer your question now specifically. You look at this peptide, and what we see in this peptide here, for example, you see E, which is a acidic amino acid residue, right? We see another E here, that's another amino acid residue that's acidic. We see S, right? And there is also H and Y. Everything else is not contributing. Oh, there's another D here. Okay, so 4 amino acid residues are acidic. So this is going to push the PI down. Okay? Because we have amino acid residues that are acidic in excess. Like the same thing with glycine, insulin glycine, where they add 2 additional, they could not change inside because it would lose the function. So they put outside 2 more basic amino acids with the intent of raising the PI so that they could aggregate more nicely. Okay? So that's all we have to do. You don't want to calculate because it's a lot of work to calculate this PI, right? You have to go one step by step. So I just want you to think about that. If this peptide were all alanine, the only thing that would contribute would be the C terms and the N terms, which is basically about 6, the average of this. Okay, so it's going from 6, it's going to be either up or down from that. And the question is always is going to be very straightforward. It's not, maybe this one here contribute more, because we have histidine 6.5 or 6, right? And this one is also 10. So we would get a little bit confused if we have too many of those. We would not be able to speculate. But when we have a predominance of amino acid residues one way or the other, I put this thing in the wrong place. It should be here, right? Should it be in D, not yes. Let me correct that. Oops, the whole thing went went up and that was the residue. So there are 4 residues that are acidic. So therefore, without calculating it, we can guess this is going to be a very low pI, much lower than 7, okay? So that was, oh, and now about the peptide planes. So what was the question about the peptide planes again?
Kind of how to identify them because I'm still a bit confused.
You still confused?
Based off their stereochemistry, right?
So first, to identify them in a plane is very easy. For example, if you decided to look at this amide bond in here, one of them, then we are going to have this CO, right? That's part of this plane, this nitrogen and this hydrogen. And then we are going to have the carbon alpha of the preceding amino acid and the carbon alpha of the next amino acid residue. Okay? So that would be a plane, which is hard to draw here because these figures are a little bit crushed, compact, but something like, something that's come to this one, this one, this one, and this one would be a plane. But your question is about the level, the angle?
Just if it's based off stereochemistry or not.
So it's because of this bond in here, this amide bond, dictates that this thing has to be in a plane. This because it's not like a single bond that would rotate. So this is almost like a double bond. So because that thing is in a plane, everything that's associated, these other atoms associated with that, all remains in the same plane. So this is the factor that causes this whole thing to be on a plane. It is characteristic of double bond that we have for amide bonds.
Oh, I see. So is it?
It forces them to be in the same plane. They cannot go out. If this was a single bond, this thing would rotate. There would be no plane. So all 180 possibility would be there. But because of this double bond characteristic of this amide bond, it holds that in a plane. And now we know that we have one plane and another plane of another bond. They are going to become like this. So they can rotate against each other, but not within. So this is going to be a series of, if you have 300 amino acids, going to be 300 planes like that. And in addition, the side chain residues. But these are going to be planes one after the other, many of those. Within the planes, there is no change, there is no rotation. But plane against plane is going to rotate at different positions. And depending on the position that they stay, they generate an alpha helix or a beta strand, or maybe nothing, just a random coil.
So they can be most easily identified by seeing the amides?
Yeah, because of the amide bond is the nature of the game. All right?
Thank you.
Anything else? I didn't bring in new problems to solve it because we already gave it 2 midterm exam and things like that. So I would like it to refresh your mind about the amino acid, right? Because this is 55% of the exam. So one is to write it there. There will be a question, maybe ask 5 or 6 amino acid residues. For one exam is going to be one question, for another exam is going to be another question. But anyhow, write the structure of these amino acid residues, 6 of them or 5, I don't remember. So you are going to be asked to write that. Now the question is that, do I write this thing the same way that the professor writes in class, see something, or do I write with the lines? Doesn't matter. Okay, as long as you write the structure of the amino acid. If you write like this here, that's perfectly fine. We prefer that when you write in the protonated form, okay? If there is a carboxylic group, it's protonated. If there is an amino group, is protonate as well. And the S is SCH and so forth, okay? So different from this type here, because this, you see, for example, this glycine, right? So you see glycine here. it does not have, it's not protonated. None of them is protonated in here, right? So we see here COOH and AH2. Yes, what's your question? Yeah.
For the rainbow configuration protein, do we have to name any particular part, or do we just have to know where the end term is? And
It's important to know what the rainbow is telling you that's coming from N to C. Because, for example, it might give a protein, and then there's lots of helix, and it says helix number 3 has such and such configuration or whatever. Some question about the number 3. How do you know what's number 3 if you don't know where to start counting, right? So that's what's very important. Know the blue and the red, that's N and the C terminus, is very important because then we can situate on the counting and everything in the location of those. Yes.
I have a follow-up question on the
Yeah.
rainbow. So when we're asked to estimate the length, so there was a question 15C on the practice that was like estimate the length of the C-terminal segment. How do we go about? I don't understand why we add like 1 to the number of residues.
I don't remember the exact mathematical term for that. I think it's inclusion, addition, or something. I don't quote me on that. Anyhow, when we count anything that we start from a number and they go on, like for example, I have 4 fingers here, right? And if I start counting this number 1, this number 2, number 3, number 4, and if I ask you, I start with number 1 and I finish with number 4, how many fingers do I have? You are going to say 4 minus 1, you're going to say 3, and it's not 3, it's 4 because you forgot to include the starter, okay? So it's a mathematical calculation. I can't remember the exact term for that.
And then when it asks for like the length of the C-terminal segment, because what I was confused about was like, I thought that I would count like the coils and then multiply that by 3.5.
Right. So when you ask the length, it might ask you different ways. For example, it might have a certain number of turns there.
Mm-hmm.
And if, let's say that the alpha helix is beautifully with 3 turns, then we are going to say, okay, 3 turns times 6, 3.6. Then I know the length of that, right? How many residues are there,
Mm-hmm.
okay? Another way of doing that, which is the common way that structural biologists do, is that starting from amino acid 21 and it goes to amino acid 41, for example, then you are just to subtract that and add 1. I don't know the specific question that you are talking about, how the problem was displayed, but it's always one way or the other. It has to give you some hints of how many amino acid residues are there. You have to figure out that to do everything else. Okay? So, for example, might ask a very common question, ask the length of this helix. So first, you determine how many amino acid residues are there. Then you multiply that by 1.5. Because it's a helix, they advance 1.5 per amino acid residue. If it was a beta strand, but beta strand was not going to be in midterm 2, because it was covered yesterday, so it's going to be in the final exam. If it was a beta strand, we will calculate the number of amino acid residues and multiply by 3.6, right? Because it's a longer one, more extended. Okay? Any other question about this? This is important. This is a very important question because it's always there, sort of. Yeah.
I think I'm just having a hard time understanding how the process of naming the different parts works.
Uh-huh.
Like alpha 3, like how do you start it?
Always you start from the N terms. Everything starts from the N and it goes to C. If you have a 5 helix, the helix closer to the N terms is going to be 1. And then the closer to the C terms is going to be 5. Okay, so everything is based on the orientation starting from the N terms and towards the C terms. Okay? Anything else? So you guys remember these fellows very well? The amino acid residues, no problem. Oh, there is some question there. Number 3 was regard calculation of PI of the peptide. I just need clarification on how to start and where to the charge from. So I don't think, I didn't write the exam, but I don't think, I don't think that there will be any question there to calculate the PI the way that I did in class to demonstrate. Remember I did in class, this is net charges plus 5 or whatever what was, I don't remember. Then I'm going to pass to the first pKa and it's going to decrease one charge and go to and make this little table. I was trying to explain how this thing comes from, but probably there will be not such a question. There could be a question like the one that we discussed before, for you to see if you can think about that without doing any calculation. Okay? I don't think we need any calculation for that. Number 10 was asked to prepare 20 liters of histidine buffer, pH 6, using histidine chloride and the monohydrate and KOH. So this kind of problems with buffer, we have to find out first what kind of buffer you have, right? So you have, for example, here we have to start with histidine fully protonated and you find out where is the pH 6, what's the equilibrium between the two species. When we have the equilibrium between two species, then we have the pH called pKa plus or minus logarithm of the conjugated base over the acid. Remember the Henderson-Hausbach equation, right? And then you calculate from that. However, I said in class already, and the people sometimes don't trust when I say things in class, there will be not so much calculation this exam. If you, for example, if you forgot your calculator at home, you are not going to regret anything. So I think this problem would require lots of calculation, right? Can't say more than that. Can you go over how to read and combine chromatography, more specifically, go number 11, material predictor. Thank you. Okay, what else? All right. Let me see here. Maybe I have a recap here of the chromatography that we did. Just waiting here because I'm displaying class, so in order for students to see that, I had to display in class the Zoom, the YouTube, and then that's a delay of 20 seconds on Zoom, so let's wait for that thing to come. So I have here the whole chromatography method in one single slide. Normally 20 seconds, but today is a little bit slow. Basically, we're going to be talking about, this is coming up. We're going to be talking about these different types of chromatography, right? Those are the important ones. So we have the ion exchange chromatography. There was a question in Piazza the other day that I answered that was completely off because the person was mixing up the protein with the stationary phase. The stationary phase is some plastic, let's put it that way, a plastic material that's sitting there inside of the column. That's not plastic actually, but like a plastic. We have a charge, and this charge on the surface is either positive or negative. How do I select this column? I select this column based on my protein. If I have a charge positive, and my protein is going to be negative, right? Because I cannot change the charge. I can buy another column and then replace it, but I cannot change the charge. But my protein, I can't change the charge. I can manipulate the pH. My protein can be positive or negative, right? So I manipulate the pH and I use the charge. So the surface of the thing and the exchange, the name of the exchange is what is the protein exchange with, right? So if the protein is negative, that's an ion exchange. Has to exchange with a chloride. So the question was, okay, there's a chloride, and therefore the column should be negative. No, if there's chloride, it's negative, right? So this column has to be positive, obviously, right? So if chloride is the exchange, the ion that's exchanged, obviously the protein is also negative because chloride is negative. So is that exchange one negative with another negative? How do I exchange? Because we put more chloride than protein. And the preponderance of chloride is what makes the protein that goes away, right? Because there's more. Now, if I have a protein that's positively charged, then my resin is going to be negative, and my ion is going to be positive, such as lithium, right? So I'm using a column and a flash of lithium because my protein is positively charged. This is about the ion exchange chromatography. Size exclusion chromatography, we recall that it's based on the size, and the larger protein do not spend much time because they don't have it. They are too big to get inside of the little spaces in the matrix, and they pass through a little bit faster. When they pass through a little bit faster, they come earlier, right? So if there is a trace of time, they are going to be in the beginning of the time, right? So we call the retention time. How much time are they retained? How much time they reside inside of the column? So the ones that are bigger are going to be the first peak to come off, right? And then the smaller ones are going to come later. And we gave in class one example that we had a dimer and a monomer, and we asked the question, which one is which? So if you have a dimer and a monomer, the dimer is obviously twice as much the monomer, so it's a larger one is going to come first, and the monomers come later. This is just the opposite when we talk about gel electrophoresis, which is a different technique, right? Have a gel, it's going to migrate differently, right? And then we talk about affinity chromatography, various examples of affinity chromatography, and always is one partner of a very strong interaction is immobilizing the column, and another one is moving. And I gave a clarification also about this protein A affinity chromatography. The antibody has this Y shape, right? The shape of the antibody. And accidentally someone discovered that this protein A binds to this part of the antibody. So all antibodies have the same part in here. So all antibodies, they bind to it. So it became a very useful protein to use because we can immobilize this protein in the column and pick up any antibody, right? But if you have a mix of antibodies, it's going to pick up a mixture because all of them are going to bind to that, right? However, when they make it in the factory, in the companies, in the pharmaceutical industry, they make it a larger quantity of this antibody. They capture with this type of chromatography because it's very effective. Pick up the antibody, normally the active side of the antibody, that we talk later in class, is in the upper part of the wire, but this protein, it binds to the stem of that wire. So it's a very useful protein. That's one example of affinity chromatography. Now, when it's bound there, it's absorbed on the column, how do you get rid of that? Because now everything that was not antibodies passed through, you have all the antibodies stuck there in the column, right? Now how to get rid of that? That's one example of the one example that I gave from previous exam, where we see that we monitor the pH, and all of a sudden the pH goes down. And then we see another peak comes off. It's the peak of the protein, because once they reduce the pH, these affinity interactions all gone, because now all the amino acid residues that the protonate or deprotonate, they change. If you have a high pH and then you lower the pH, you have lots of protons available, everything becomes protonated. So now, if this interaction involves, for example, a histidine and an acetate, aspartate, for example, now the histidine is going to be protonated, it's going to make this interaction. But some other interactions are going to be lost because you protonated it. Okay? For example, if you protonate too heavily, even the aspartate and glutamate, they are going to be protonated. So they do not make this interaction anymore. In other words, every time that you change the pH, you change all these interactions. So the protein has no affinity for protein, the antibody has no affinity for protein A anymore, it comes off of the column. Okay? And then we use the various examples in class with a histag, where we immobilize a nickel, and we use histidine to bind to nickel. We use various examples of those, but all the same principle, right? That you get stuck with something and then we remove that later, right? one example that I present in class that the was I presented this animation in class, and then I took a still image of that, and wanted to ask what's going on in that still image. So in class I presented the animation to see in real time, and there was a case of chromatography, one of the animations that I showed, and I asked later on in an exam, for example, this one here. I gave this picture in class, in the exam, and I asked, what kind of chromatography is this? And just by saying ion exchange chromatography is not enough. Don't get anything, because this is obviously ion exchange chromatography. We have lots of charged things in here, and we see the sequence that they are coming, right? Or this guy here are coming. You see this one here comes first, and this one here comes the last one to come. And what we see about that? We see that these guys are large negative charge, first one to come out. Net negative charge, okay, second one. Then we have a net positive charge and a very high net positive charge. So which one was retained the most? The top one, right? So if this guy was the most retained one, what we expected, the resin is going to be positive or negative? Negative, right? So that's going to be negative, the resin here, right? And these guys are positive. Right? So it's a cation exchange chromatography, because when you exchange things that are positive, first we figure out what the resin is, and then we can tell what is the kind of exchange it is, right? Because it's the opposite of the resin always. But if you don't look at the detail, you cannot figure out what's the charge of the resin. Is it okay? Yeah? Any question about that? Let's see if I have some other slides here. Oh, this one here is about the COVID test that we talk in class. Does everyone understand this thing well? Yeah? Oh, Jane, you had a question. I skipped the question. What was the question?
Yes, answered it.
Oh, yeah, already. Okay, address that. Yeah. So this, the COVID test. The COVID test utilize antibodies that are stuck there, and utilize antibodies that are labeled, and utilize secondary antibodies. Secondary antibodies are antibodies that bind the antibodies in general. Okay, they bind the antibodies. So you have this antibody, and I think one time that I asked this question, I gave you the lane, the gel here, without any marks, and I asked you to put the labels and what was sitting there, right? So here is going to be both of them are going to be immobilized. They're going to make this line. That's the line that we look at there. It's the same thing like a pregnancy test, right? The same thing. A line there, and you have to follow. And you have to have two lines because one is control. Let's say that the sample was bad. You put it there, and, oh, I don't have COVID. No, your sample didn't have COVID, but you didn't take the proper sample, right? So we have to have the sample because the controls, because then we're going to see, yeah, the control is there, but the test doesn't show anything. Therefore, the sample was good, right? So this is what's going to give us a control, is this line here with the secondary antibody. Because no matter what, some antibodies are going to pass in here and they get trapped by the secondary antibody. So it's going to light up here. And in order to be seen, the antibody has to have a label, because we cannot see antibodies. Only a label when they bind, they illuminate, they generate color that we can see, right? But if there are antibody without any label, we will not see anything. All right, so no matter what, they're going to pass in here. But if they are bound to a piece of the virus, then when they pass in here, this guy here, I want also this virus. I want this molecule. They like it as well, right? This guy here don't care. They don't bind to this molecule. They bind to antibodies, not to the virus molecule, to the protein from the virus. But this guy's bind, and the fact that the other one is bound doesn't say anything to them. They still want to bind, so they make a complex there, right? So these antibodies here are not immobilized. They are mobile. They can move. So when you put the sample there, they're going to move, and as they move, if they are bound to a piece of the virus, they are going to be captured in the first lane. If not, they are going to pass through, and they capture in the second. Anyway, so no matter what, the second line is going to be activated, and maybe the first line if you have an infection. Is that okay? Do you have any other question on that? Looks almost the only one asking questions. Can you go how to read and combine chromatogram more specifically? Can you go over number 11 on the material you posted? Yeah, so again, these are difficult to say what question I'm talking about. Are we using calculators for the exam? Like I said, you should bring your calculator, but if you forget that, you're not going to have any trouble.
I have a question.
Yeah.
For the zinc and the cysteine B10,
Yeah.
to bind the hexamer, so we need two zinc to bind to make hexamer, right?
So we're talking about which one?
The
About
insulin?
insulin.
Yeah.
Insulin. Okay. Oh, insulin is here. Let's talk about insulin. Okay. So insulin is a very important molecule. So everyone knows someone, or maybe even might have suffered from diabetes, right? So everyone knows someone who has diabetes, right? So diabetes is a very important issue, and insulin is part of it. Either because they don't produce insulin or because they produce insulin, but the system doesn't, the receptors are insensitive to insulin, and so many other examples, right? So what did you talk about in class? What are the major points about insulin? One is that insulin is not made as it is needed, right? It's made in a bigger package, and then they will wrap the package and deliver insulin when needed, right? So the body is going to make pro insulin, and until arriving insulin, there's going to be two major post-translational modifications. What are post-translational modifications? Post-translational modifications are chemical reactions that happen after the gene is translated. Okay, there is a translation, and after that, after they put the amino acids together, one after the other, then there's some chemical reaction that, for example, phosphorylation. We didn't talk much in class about phosphorylation, but we mentioned phosphorylation. Some tyrosine, for example, may be phosphorylated, right? What other kind of important phosphorylation modification that we talk about? Disulfide bridge, right? Disulfide bonds. Disulfide bridges are very important for keratin, right? Keratin and many other processes in life, but we talk a little bit in details about it. Keratin. Speaking of keratin, you don't need to know all these details. Sometimes I struggle to say, do I say this in class or not? Because if I say students want to memorize it, if I don't say, the material looks a little bit boring because you don't know where it comes from. So all the point of the hierarchy of the keratin formation is to show that that's a very complicated thing that starts with two molecules of keratin and then goes all that way, that complication. There are many different disulfide bridges there. But the point for us is the molecule that we're looking at, the keratin, that they form disulfide bridge, right? So disulfide bridges are very important there. What's the post-translational modification most important for collagen formation? Collagen. Yeah, but what is the post-translational modification there? Yeah, so they're hydroxyproline and hydroxyalanine, right? Lysine. So these two amino acid residues have to be hydroxylated. They have to be modified after the protein is prepared, right? And that is associated with vitamin C, because vitamin C is a cofactor, and that enzyme that is associated with the iron 2 and iron 3. But we go back to that. So here we have two post-translational modifications. One that are going to digest this peptide, right? Cleavage of this peptide, different place, as shown here in the cartoon, in the two places. This red part is going to go out. And only the red and the blue are going to stay together. So first they have the first post-translational modification is that they form this disulfide bridge. And then they digest the peptide. So basically they make proinsulin as a larger molecule and they have insulin ready as a smaller molecule. Now, then the question is that how this thing works. This insulin is not a single molecule that's there. It's the only molecule, this monomer, is the only one that activated the receptor. The receptor do not bind to a dimer, tetramer, or a hexamer of insulin. But inside of the body, insulin aggregates. These molecules get together to each other and they form a complex. And that complex has to be dissociated in order for insulin to be active. So in the case of the insulinoglycan, the beauty of it is that they form an aggregate that throughout the 24 hours is little by little releasing that, right? There are many drugs that we take these days that they are either you take one pill and it lasts for 6 hours, or maybe you take one pill and lasts for 24 hours because they have a slow release, right? In case of insulin, the slow release is based on the aggregation. You aggregate and slowly remove from that. So the question was about the zinc in here, how that works, right? So this has two, the monomer has two chains, A and the B being the short one, and the B has two histidine, at least two, and there's two histidine, and the histidine number 10, that's the one that binds to zinc. So there's each a part of that, each part of the monomer, one monomer bind one side, another monomer bind another zinc, and then they form this complex, and then more and more. So a total of 6 of them graph together, and they stay a complex. Okay? So I think the most important question here is not this aggregation or anything, is to keep in mind that aggregation is good to release slowly. It's not good to activate the receptors. Because if you have insulin that's there, aggregate, is not going to do any good. Like I mentioned in class, if a patient comes to the emergency room with a high dose of sugar, 300 milligram per deciliter of sugar, that's a huge amount of sugar in the body. And then going to die the person if they don't do anything. So if they inject insulinoglycan, it's not going to do any good because you want immediate action to lower the sugar to a certain level, and then you manage from there, right? First, make sure that the person stay alive, and then continue to be alive. Right? So first we shut down, and then we want insulin that active very quickly. That's when insulin aspartate, because they change one proline in an aspartic acid, so they reduce the aggregation, which is natural. There's still already some aggregation there, minimum, but it's there. Now they reduce it so that insulin becomes more readily available. So when they inject, it immediately active on the receptor, right? And resolve the problem. No other question here? Oh, and back to the question about now the question with the vitamin C. Vitamin C is very important in terms of collagen, because if you don't have vitamin C, we're going to get in trouble, right? because we are not going to be able to form hydroxyproline and hydroxyalanine. So therefore, your collagen are not going to be good enough, right? And if collagen is not good enough, there are very serious problems, not only joints and so forth, but many organs that utilize collagen as the structure. So what happened with that is that we have an enzyme, and in the case of the picture here, because they were not able to use the iron for that, they use cadmium as a surrogate, but the principle is the same. They make this complex here, and this iron would be iron 2 in this enzyme. This enzyme is made, you know, and we talk about in class also, that some proteins utilize some organic molecules and the ions to get together to make it functional. Okay? Only the 20 amino acids are not enough to make everything that we want. So you have to stack some other organic molecules, some ions to do whatever job you want to do. One of them is iron 2. Then, when this enzyme process proline to hydroxylate it, this iron 2 becomes iron 3. Okay? And iron 3 is not active anymore. So this enzyme needs to be recovered. And the cofactor for that is vitamin C. Vitamin C would reduce this atom, this iron, back to iron 2. So if you have enough vitamin C, your enzyme is going to be happy because it makes this reaction and it comes back and they do another reaction, back and forth. If you don't have enough vitamin C, this enzyme is going to do one reaction and it dies. This enzyme is unable to do the job anymore. And then you can imagine you have all this molecule that we make, large, big molecule, that we spend so much energy, put all this thing together, and you dump with the first reaction. It's the same thing like smoking. Sometimes people smoke, this carbon monoxide that they inhale, there's always a little bit of carbon monoxide, they inhale. Each molecule of carbon monoxide kills one molecule of hemoglobin. So that's why people that smoke sometimes they are deficient in oxygen, right? Because they smoke and then they destroy each molecule of hemoglobin, CO, carbon monoxide, one molecule of hemoglobin is dead. It's still circulating in the blood, but doing nothing for you. In your normal life, they pick up oxygen and deliver carbon dioxide and go back and forth, and they do that for 3 months. Now, if you smoke, you kill it, you stay dead there, and for 3 months you have to wait to make a new one, and then you keep smoking it. And doesn't matter if it's cigarette or marijuana, it's the same thing. Any smoke that you inhale would do the same effect. That's why people are so scared about smoke in the house, right? We have smoke detected. Because smoke we cannot detect very easily, and the people tend to go sleep when the sensation that they're going to sleep, and then we never wake up, right? So that's why it's mandated to have smoke detector in the home.
I'm not sure if you mentioned this, but the Fe2 plus and the Fe3 plus, what enzyme is it in and what reaction is it
So
in?
the name of this enzyme is for proline is proline for hydroxylase, and the business associated with vitamin C here is the iron 3 going back to iron 2.
Yeah.
Okay, so reduction of the iron.
And what is this enzyme catalyzing?
The enzyme
The
catalyzes the
hydroxylase.
reaction. When the protein is made, they make proline, right?
Mm.
And then these enzymes are going to catalyze the reaction that changes this proline into proline hydroxide.
Okay.
So that reaction involves this enzyme, and that enzyme needs help to go back. Clear? I think this is important for tomorrow. I think that's all. I didn't bring much today. I just want to answer questions. And do you have any other questions? All right. How do you guys feel prepared for the exam? You feel good? Well prepared? I didn't get a very straightforward answer here. Not so confident. I think it's very important to be confident in an exam, you know. I know this material, and I'm going to show it today. I think it's going to be much better than the midterm one. But again, don't think that this is going to be final exam is going to be the same line. I think there is a very clear pattern that this goes in terms of difficulty of the exam. Midterm 1, midterm 2, and then comes the final exam that's in between the two of them. Okay? Because it involves also some calculation for the final exam. And it also encompasses the whole material. Okay? You guys like to see each other in there? Not to be. Anything else from the what's that? Can you post the notes on the board, please? Yeah, I think so. There was not so much notes, but I can put this material there and a link to the video. Do you need any other help or can you read it ready for tomorrow? Any other midterm exam tomorrow? Or just this one? Just one? No, two? Two exams? Early in the day? Yeah, cannot be later than that, right? Did any of you attend the thing from yesterday? You did, right? Yeah. I saw some of you there. Good. All right, so good luck tomorrow. I hope you do well. And looks like you are going to be doing well. Have a good day.